Hey, my name is Aobo Lee. I'm a postdoc at UNC Chapel Hill. It's my pleasure to introduce you the KamLAND-Zen 800 status and progress with the artificial intelligence powered analysis. Here is the outline of my talk. I will give a very brief review of the neutrino-less double beta decay or zero new double beta. And then I will talk about the KamLAND-Zen experiments. Then I will talk about the artificial intelligence powered analysis KamNet. And lastly, I will give a summary of my talk. In nature, certain radioactive isotopes undergo a specific decay mode called double beta decay. In double beta decay, two beta decay happens simultaneously within the nucleus, emitting two electrons and two electron antineutrinos from the core. Neutrino-less double beta decay is a hypothetical process where a double beta decay happens without the emission of neutrino. This means that the two electrons emitted from the nucleus at large angle will carry all the energy from the decay. Thus, if you measure the energy spectrum of the emitted electron, you will find a tiny peak at the very high energy end of the normal double beta decay energy spectrum. The search for neutrino-less double beta decay is to search and prove the existence of this tiny peak. Neutrino-less double beta decay is important because this process itself is lepton number violating, and it would also imply the Majorana nature of neutrino, thus opens the gate to physics beyond standard model. Neutrino-less double beta decay is a major physics goal of KamLAND-Zen, but that's definitely not the only thing we do in KamLAND. There are some other exciting KamLAND physics topics I would like to encourage you to attend on those posters and talks. KamLAND-Zen is a liquid scintillator detector located in KamLAND mine. We reuse the old KamLAND infrastructure, which contains 1,800 PMTs, constituting to 34% photo coverage. The major invention in KamLAND-Zen is the mini balloon. The mini balloon is a 25 micrometer thick nylon film fabricated in a class 1 clean room. It is highly transparent to the light we would like to detect. After deploying the mini balloon into the KamLAND detector, we perform a procedure called xenon loading, where we load 91% enriched xenon-136 double beta decay isotope into the liquid scintillator inside the mini balloon, and we call this xenon liquid scintillator. We use this approach because the purification is well established, and xenon-136 is a chemically stable noble gas. KamLAND-Zen is split into 3 phases. The pass phase, KamLAND-Zen 400, deploy a mini balloon of radius 1.54 meter. Within this mini balloon, we managed to load a xenon mass of 320 to 380 kilograms, and the data taking spans 2011 to 2015. After combining the phase 1 and phase 2 results, our half-life sensitivity of xenon-136 neutrino-less double beta decay goes to 1.07 times 10 to the 26 years half-life limits at 90% confidence level. This is one of the world leading results, and we have published this in the PRL. The present phase, KamLAND-Zen 800, deploy a mini balloon of radius 1.9 meter. In this larger balloon, we managed to load 745 kilograms of xenon, as the data taking starts on January 2019. So targeting sensitivity for KamLAND-Zen 800 is 5 times 10 to the 26 years, and the result will be available soon. In the future, we plan to construct a brand new detector called KamLAND-Zen. The goal for KamLAND-Zen is 1 ton of xenon mass and 100% photo coverage. We currently have several R&D underway for KamLAND-Zen, and the target sensitivity is 2 times 10 to the 27 years. Starting 2018, we manufactured the balloon for KamLAND-Zen 800. We first wash each part of the film separately, and then welding all the part of the film together using a welding machine. Then we perform a helium leak check on the balloon surface and repair any leak we find. And then we fold the balloon and place it into a box for shaping. On May 2018, we bring the balloon to the KamLAND mine and deploy it into the KamLAND detector from the top, as you can see on this picture. After about 6 months of liquid scintillator purification and xenon loading, eventually on January 2019, we started the first data taking of KamLAND-Zen 800. Thanks to the very careful manufacturing and cleaning procedure of the balloon film, we actually reached an unprecedented low background level on the balloon film. Our uranium chain contamination is 3 times 10 to the minus 12 gram per gram, while the thorium chain contamination is 4 times 10 to the minus 11 gram per gram. This actually corresponds to a 10 times reduction compared to the KamLAND-Zen 400 miniballoon. Looking at this very preliminary fitting results, you will find that in KamLAND-Zen 800, the uranium and thorium contamination from the film actually goes below the solar neutrino floor. Thanks to this, within our region of interest, most of the events are now xenon-136 2 new double beta decay events. After dealing with the balloon film backgrounds, the next important background to deal with is the xenon liquid scintillator background. To suppress this background, we designed 2 cuts. The first cut is a radon cut, utilizing delayed coincidence to tag bipole 212 and bipole 214. The second cut is a spallation cut, aiming at removing event correlated with the incoming muon. So the spallation cut utilizes a triple coincidence tagging scheme. The first coincidence is a muon track. The second coincidence is the event happening within the half-life of the radioactive isotope, in this case, carbon-10. And the third coincidence is a 2.2 MeV gamma. Like most other experiments in the community, we use both a frequentist fitting and a Bayesian fitting to quote our final half-life upper limit. So on this slide, I show the spectrum of the fitting results from both methods within our fiducial volume at 157 centimeters. With a 246.1 kilogram years of exposure, the frequentist fitting quotes a 90% confidence level upper limit of 4 times 10 to the 25 years, while the Bayesian fitting quotes 4.3 times 10 to the 25 years. So the frequentist and Bayesian result agrees very well. I would like to remind you that this result has been shown on the previous TAUP meeting in 2019. So since then, there has been a lot of updates on our analysis. First of all, now we have nearly twice the exposure, aka 419 kilogram years to analyze. We are also considering a time-bin analysis on both the frequentist fitting and the Bayesian fitting. We also conducted a Fieldman-Cousins analysis on the frequentist result to check the coverage of it. And we are working really hard to finalize the analysis, and our new result will be available soon, so please stay tuned. I would also like to redirect you to the 2 posters by my colleague Takeuchi-san and Kamei-san, who will also be talking about our zero new double beta analysis. So shortly after our TAUP 2019 result, we find that there is a type of background that we did not take into account in that analysis. Those are the muon spallations on the xenon-136 nuclei. We perform a FLUCA simulation, and we find that the spallation of xenon-136 nuclei produce radioactive isotopes with very high mass number. These isotopes undergoes a beta plus or a beta minus decay. And if you look at their decay energy spectrum, a lot of them will leach into our region of interest. Thus, this background becomes the dominating background in our ROI. So as I mentioned earlier, a typical way of tagging a spallation product is using a triple coincidence cut. But those xenon-136 spallation products are generally long-lived. Their half-life ranges from a few hours to a few days, making the coincidence tagging very tricky. We designed a day-long long-lived spallation tag to remove about 40% of those events. But if we can find a method to tag and remove those events without coincidence, and that would be the remedy for those background in our region of interest. So is it possible to perform a non-coincidence particle identification or background suppressing? The answer is yes, with the help of artificial intelligence. KamNet is a state-of-the-art neural network model we designed for KamLAND-Zen. Its motivation is to achieve particle identification without coincidence tagging or hardware upgrade. In order to achieve this very challenging goal, we have to harness all symmetries in a spherical liquid scintillator detector data to reach the state-of-the-art event classification performance. The input to KamNet is a series of 2D spherical heat maps indexed by time. So here I show 4 heat maps at different time indices. And we feed those heat maps into the KamNet, which is a neural network. And KamNet will spit out a single number as a classification score for each input event. In KamNet, we would like to address the important symmetries embedded in our data. The first symmetry we would like to address is the spatial temporal symmetry, which is the spatial and timing correlation among different hits. This is addressed by a convolutional LSTM model, and we use an attention mechanism to further boost the performance of this model. Attention mechanism helps LSTM to zoom into the scintillation peak, which contains most of the information. It also provides an attention score, which helps interpreting the decision of KamNet. The second symmetry we would like to address is the spherical symmetry, which is addressed by a spherical CNN model. Spherical CNN analyzes a spherical image with rotational invariance. Thus, it greatly boosts not only the efficiency, but also the robustness of KamNet. So the KamNet result is shown on the bottom of this slide. We can see there's a magenta xenon 136 spectrum with respect to the KamNet score is clearly separated from all type of background. This means that KamNet can not only efficiently reject long-lived spallation product, but also other important backgrounds like bismuth-214 or carbon-10. While accepting 90% of the zero-new double beta events, KamNet rejects 30% of the xenon liquid scintillator background, including the long-lived spallation product we talk about, and also 60% of the mini balloon film backgrounds. The rejection power comes from the topology and the PMD hit time of single events, rather than the coincidence tagging between events. Thus, KamNet's rejection power is multiplicative with the existing long-lived coincidence tagging scheme. Even better, the increased rejection of backgrounds on mini balloon film allow us to expand our fiducial volume from 157 centimeter to 165.8 centimeter without increasing our background level. This results in a 17.7% gain on exposure without any hardware upgrade. The manuscript of KamNet is currently under preparation. At this point, you may want to ask, why is KamNet so efficient? What is it actually looking at? To answer this question, we'll need the help of attention score. Attention score can be thought of as a relative importance measure KamNet placed on different parts of the events. A high attention score means KamNet pays a lot of attention on this part when making decision, and the low attention score means KamNet doesn't really care about this part when making a decision. So let's see, when KamNet is rejecting a bismuth-214 events, it's paying a lot of attention to the falling edge, this region. So why does this happen? The reason is because a neutrino-less double beta decay events are what we call the strictly single vertex events, meaning that all its energy is deposited in a very localized region. However, most of the xenon liquid scintillator backgrounds are a beta plus or a beta minus decay, followed by a gamma cascade. Thus, xenon liquid scintillator backgrounds are closely spaced multi-vertex events. Part of the event energy is deposited by one or more cascading gammas that slightly alter the PMT hit time distribution. KamNet, harnessing all the symmetries from our data, is so powerful that it can detect and use that information to reject backgrounds. So now, if we look back at this bismuth-214 attention score plot, we understand now that this region is where the cascading gamma happen, and KamNet is paying attention to this region to reject bismuth-214. Even better, if a background event undergoes a beta plus decay, there is another mechanism called orthopolytronium, which deposits energy at an even later time. That's why when KamNet is rejecting a carbon-10 event, which undergoes a beta plus decay, you see that the last bin has a very high attention, which means that KamNet is aware of the orthopolytronium. If you are interested in more of the KamNet interpretability study, I would redirect you to a poster of my colleague Ha-Sung Song. So here is a photo of our collaboration before the pandemic. So we are a collaboration containing scientists from Japan, from US, and from Netherlands. And here is a summary of my talk. I will leave it here for you to read it. Thank you for your attention.